I just started streaming. Well, I know the audio is working because I just heard my dog barking. All right. Okay. All right. We are back. I'm sorry. I'm trying to bring the energy. Like, I have this YouTuber, his opening is like, all right, and we're back for another. He comes in just like that every time, and it always makes me laugh. I'm like, yo, why is he talking so high pitched and loud? It's so funny, but he brings the fun, brings the energy. Anyway, so welcome YouTube, welcome scholars, beautiful mind here, and we are moving forward with our progression of College Algebra 1 with Morris Brown College. So this is our second stream for Chapter 1 on problem solving and critical thinking, and this will be section 1.2, estimation graphs and mathematical models. All right, okay. So let me see. That'd be nice if I can. I'm still like a little bit perturbed by these little side things, but I think we're okay. Yeah, I think it's fine. So some objectives here. We like to use estimation techniques to arrive at an approximate answer to a problem. Apply estimation techniques to information given by graphs. We like to develop mathematical models that estimate relationships between variables. Okay. So estimation is the process of arriving at an approximate answer to a question. Methods of estimation are rounding numbers, using graphs, and using mathematical models, right? So whenever we're doing estimations, we're not trying to be exact. A lot of times it's like mental math, or you just want to be within some range. You want to be close. You don't have to be exact for this, right? So for instance, when we're talking about rounding whole numbers, first we like to look at the digit to the right of the digit where the rounding is to occur, right? If we're rounding to the tens, to the right of the tens will be the ones. You know, so whatever place you're trying to round, you look to the right of that number. If the digit to the right is 5 or greater, add 1 to the digit that's to be rounded. Replace all the digits to the right with zeros. If the digit to the right is less than 5, do not change the digit to be rounded. Replace all the digits to the right with zeros. This squiggly equal sign means is approximately equal to. All right, so I think in the past, we may have articulated it like, okay, when you look to the number to the right, if it's 5 or greater, you round up. If it's below 5, we would say you round down, but I like this articulation better where it says, don't change the number that you're rounding and then replace all the digits to the right by zeros, right? I like this articulation better. It's more accurate because a lot of times what happened before, when you say round down, then the students will subtract 1 from the digit. You're not supposed to do that, right? It's either the digit in question is going to stay the same or it's going to round up, right? So those are the only 2 options. So example of rounding a whole number. Round the world population to the nearest 100 million. Okay, let's go like this. So to the nearest 100 million. Let's see, I like to kind of go like this. Let me see. So here's our thousands place. So here's our million, 10 million, 100 million, right? So 100 million, that means we're looking, this is the number that we want to consider rounding. So we need to look to the right of this number. So to the right of the digit 4 is 7. Because 7 is larger than 5, this 4, we round it up. We add 1, right? So then, let me see, 1,000 million. So it should be 7,500,000, right? 7,500,000. Then, basically everything, all the digits to the right are all zeros. You see it here, 7,500,000. I feel like there is some way to suppress this, and I just don't know how to do it yet. Like, even if I can collapse it to just a point, that would be great. That's all I really need, because it's kind of like in the way. Let's see if I can go like, there might be a setting or something that I have to like find and change, but let's go with it. So round the world population to the nearest million, right? So here's our decimal, here's our thousands. So this is our millions right here, right? So the nearest million, if we look to the right of 6, is a 2. Notice that 2 is what, less than 5. So then the 6 stays as is. So then the final result is going to be what, 7,476,000,000, and then everything else is a 0, right? So all of these digits go to 0, and the 6 stays as, I don't know why I keep saying 6. I'm also just waking up. I was in a deep nap. So 7,476,000,000. You see it here, right? All the digits to the right became 0. Okay. So again, hopefully you're watching this before we meet. Like I said, my goal is to get these videos, make these videos available before we meet, so you can watch them in advance. So that way, when we meet, you can come with questions. You can question. You can email me or ask questions about this, like via email or whatever. But if I don't respond, promptly, then just ask me during class, right? And we can talk about it, especially if it's something for that week or whatever, Okay. So around the world population to the nearest 100,000, right? So if we're in the thousands, here's our 10,000, here's our 100,000, right? So this is our 100,000. To the right of this digit is the 4, right? Because 4 is less than 5, that means this 2 stays as is. Remember, our only options, either the 2 is going to stay as is, or we're going to add 1 to 2, right? And then the rest of these digits get replaced by 0. So then we're going to have 7,476,200,000. You see it here. 7,476,200,000. The first 7 digits of pi, right, this symbol here, the mathematical symbol pi, are 3.141592. Round pi to the nearest hundredth, and then to the nearest thousandth. So when it comes, to the left of the decimal is the ones place, but when it comes to the right of the decimal, there's no ones place to the right of the decimal, right? So as we move to the right, it kind of skips over 1 and it goes tenths, hundreds, thousandths, 10,000ths, 100,000ths, millions, right? So if we want the nearest 100th, 10th, 100th, so that means we're looking at the 4, right? So the 4 is a number that we want to round. To the right of 4 is a 1. Because 1 is less than 5, that means the 4 stays as is. So then to the nearest 100 should be 3.14. Okay, 3.14. And then to the nearest thousandths, tenths, hundreds, thousandths is going to be that third decimal. So this is the decimal in question. To the right of 1 is a 5. Because the digit to the right of 1 is 5 or greater, we're going to add 1 to this guy. So then we get 3.142 thousandths. All right, so we said 3.14 and 3.142. It's at 3.14. Here's at 3.142. Okay. So not too terribly bad so far. Okay, estimation by rounding. We purchased bread for $2.59, detergent for $5.17, a sandwich for $3.65, an apple for 47 cents, and coffee for $8.79. The total bill given was $24.67. Is this amount reasonable? To check, round the cost of each item to the nearest dollar, right? So for the bread, that's going to be what, $3? Detergent, the nearest dollar would be $5, so that brings us to $8. A sandwich for $3, the nearest dollar is going to be $4, so 8 and 4 is what, $12? 47 cents rounds to 0, so we're just going to let that be. We're still at 12 right now. And coffee for $8.79, the nearest dollar is 9. That brings us to $21. Okay, so the total bill was given here, so it is reasonable. We got 21 when we estimated with rounding. I feel like I'm missing something. That's 4, that was 5, 3. We got 21. Okay, so let's look here, right? So then 3, you see the $21 here, okay? So to check, round the cost of each item to the nearest dollar. It seems high compared to the $21, to the $21 estimate. Adding the prices of all 5 items gives a true total bill of $20.67. Interesting. So maybe that's tax or something, right? So, because notice that even when I did my estimate, I paused because I was like, well, wait a minute. It was $3 more than our estimate, you know? And then, so then to account for the $3, maybe it's tax. That could be tax that caused it to spike so much, all right? That was interesting. Because at first I thought I made a mistake. I was like, wait a minute, why is my estimate so much different from this bill? I was like, are there some hidden fees or something? So then you might want to go back, try to figure out, well, why is there such a difference in price, right? So $4 in taxes, that doesn't sound right. Or $3 to $4 in taxes, maybe. Because what, 10% would be $2. So 1%, 20 cents? Yeah, that still seems kind of high. I don't know. Because even if tax is usually not, tax is usually like 7 or 8%. If it was 10%, that would be $2. I mean, I don't know. Yeah, I don't know. They could have snuck something in. Yeah, that's kind of strange. I don't know why. Maybe they ranked something up improperly. Maybe we got double charged, or maybe the price of something wasn't listed properly. All right. Anywho, so circle graphs. Circle graphs, also called pie charts, show how a whole quantity is divided into parts. Circle graphs are divided into pieces called sectors. The figure on the next slide shows a circle graph that indicates how Americans disagree as to when old age begins. Now, personally, I feel like old age begins when it's a combination of mentality and functionality. It's not. I don't think it's limited to chronological age. It's like when your mind starts to slow down and you can't, your functionality is lessened, right? I was just sharing with my mom. I was like, we was just talking about overall health, and I was sharing with her like, there are people that are like older than her, but that move better than me. I mean, like one of them is my boxing coach, and I'm just like, it's to me, it's a state of mind. It's something like in your mind that you have to take charge. That's okay. So Americans' definition of old age, let's see. So we have a decline in mental functioning, right? Okay, which is 32%. A decline in physical ability. So between physical ability and mental functioning, that makes up about what, 73%, right? Becoming a grandparent. Nope, I know grandparents that young and sprite. Retirement, okay, maybe. I don't know is 1%, reaching a specified age. This is an interesting chart. So according to the U.S. Census Bureau, in 2016, there were 345,624 Americans 25 years and older. Assuming the circle graph on the previous slide is representative of this age group, use the approximate information displayed by the graph to determine a calculation that shows you the number of Americans 25 years and older who define old age by decline in physical ability. Use rounding to find a reasonable estimate for this calculation. So let me see. In 2016, there were 219 million Americans. Maybe an easier number would be 220 million, right? 220 million. Use the pie chart or the graph to find the number of Americans 25 years and older who define old age by a decline in physical ability, right? So if we have 220 million and physical ability, 41% of those, right? So if we're saying 41% of that 220 million will give us an approximation for the number of Americans that have this philosophy, right? So then what we can do is like maybe 0.41 times the 220 million. And again, 220 just seemed like an easier number to deal with than this. This has too much going on, right? So you can either say 0.4 times 220 million or 0.41 times 220 million, right? Either one of those will work, right? And you see it here, 0.41. Now this is going to give us this isn't an approximation. This is like, okay, how we can find that number based on the chart. And then for part B, right here, see, round 41% to the nearest 10th, which would be 40%. And then this one to the nearest 10 million, 220 million. So then we get 88 million, approximately 88 million Americans, 25 years and older, define old age by a decline in physical ability. Okay. So this is like if we were trying to be a little bit more precise, and then if we just wanted an approximation, 40% and 220 million. Okay. Man, it is like dark outside. It's only like 4 o'clock. I guess we got like a storm or something coming through. I hope everybody's staying safe. And like with all this, like everything is just so chaotic right now between the weather, all the stuff going on with Trump. It's like finally, like just because, not that the Republican, I'm less concerned about that. It's more, I got tired of him just taking advantage of everybody, not paying workers and like thinking that he can just say and do anything. I was like, bro, you can't just say and do anything. Like everybody has to be accountable for their actions. And like a lot of, like he's making it worse. Like he keeps just saying stuff and it keeps making his situation worse. If he just stops talking, things would be a lot better for him, right? But I mean, it is what it is. Let's see. Is in my way. Estimation of graphs and bar graphs. Bar graphs use a vertical or horizontal bar to represent each item. The length of the bar determines the amount. We can use bar graphs to make predictions. The bar graph on the next slide shows the life expectancy in the United States by year of birth. Okay, I feel like that's not too bad. Life expectancy in the United States by year of birth, and then I think it's male versus female. So the male is like this pink, I guess, and the females are, I don't know if that's orange or yellow. I'm gonna say yellow. So I feel like I just had like not an invasive thought or not an intrusive thought, but more like a stoner thought. Like, how do I know that what yellow looks like to me if I was looking through somebody else's eyes? How do I know it doesn't look like purple or some other color, right? And like, how do I know that the way I see colors is the same way that everybody else sees colors? And like, there's some merit to this question because, some people are missing like rods and cones in their eyes. And so they see black and white, like they can't see color. And then some people have extra rods and cones. And so they see colors that nobody else sees. And some people have this thing, I think like Kanye West and so a few other, there's a good amount of people, a lot of like artists. They have this thing called like, there's another guy I follow, YouTuber, his name is Billy Carson. I think he has it as well. But it's this thing called, I think it's synesthesia, where they can see sounds as colors, right? So I've always wondered that, like, and like, because like my dog can clearly see things, like when I watch her, she can clearly see things that I can't see. She be looking around the room and following stuff like she's watching a movie. And I'm looking and it just be space and dead air. I'm like, what is it that she can see? And then like I've had experiences where she clearly can smell spirits. Like I smelled it for a little bit, but it's like, how do we know what her experience is? Like, because we can't, you know, we can't smell through her snout. We can't see through her eyes. So we don't know what she can and can't see. We don't know what she can and can't smell. We don't know what she can and can't hear. Like, I never even thought about her being able to hear interdimensionally. Like, I know she has like heightened hearing, but this is the first time I've ever considered, well, damn, can she hear in other realms as well? That's why she be barking so much. So I just use her, even though she's a Chihuahua, she's obviously not gonna like fight like that. You know, she's not a big dog, but I use her more for an alarm system. So she lets me know if anything kind of comes within a certain range on this plane or another, because she clearly can see something that I can't see. I liken it a lot to the movie Coco. So anyway, we went on our little. You're gonna have to bear with me with these tangents. They just always they're interesting to me and they make me smile. So it is what it is. But yeah, we went into that because of the colors, and I was just curious, like, how do I know what I see as red doesn't look green to somebody else or whatever? Just a random question. Okay, so we got this bar graph. We have the birth year on the bottom. This is behaving as expected. You would think that over time, technology would get better, so people would live longer. So the bars do seem like they're getting longer over time. So, you know, that kind of goes with what you would anticipate. Okay, so we're gonna move forward. So in this example, it says applying estimation and inductive reasoning to data in a bar graph. Estimate a man's increased life expectancy rounded to the nearest hundredth of a year for each subsequent birth year. I feel like something is missing. Life expectancy rounded to the nearest hundredth of a year for each subsequent birth year. Subsequent from. So these are by the decades. Birth year. So what, they want like 2030? If we look at the men, so that went up by 1 year, almost 1 year, almost 2 years there, almost two, about two. That was one. So maybe like 78.1 for 2030, increasing it by about one, it looks like. Okay, so let me see. Estimated man's increase to the nearest hundredth of a year for each subsequent birth year. So they're found in the slope. Let me see. 77.1 is 2020, 65.6 is 1950. And again, so they're finding the slope between the first and the last. And so they get 0.16. So then for each subsequent birth year, oh, okay, I get what they're doing now. Okay. For each subsequent birth year, man's life expectancy is increasing by approximately 1600th of a year, right? So long story short, they found the slope. They chose the first and the last pieces of data for the men to find the slope. And then slope is the rise over the run, which is the change in Y over change in X, right? So for 2020, the life expectancy for men were 77.1. In 1950, it was 65.6, right? So that's what the numerator, that's the change in Y. And then the change in X is 2020 to 1950. Right? So that's where this came from. Okay, that makes sense now. Estimate the life expectancy of a man born in 2030. So we would anticipate that it would increase every 10 years by that 1600th of a unit, right? So we should be able to say 77.1 times 1.16, right? Because you want to increase it by 16%. if you say times 0.16, that's going to give you 16% of 77. So we want to take that result and add it back to 77.1. So long story short, we should be able to do 77.1 times 1.16. They did the 65.6. I guess it would still work out to be the same. Let me do a quick calculation. So they use the 65, and then that's 80 years. That's when. Oh, that's part B. Okay. Well, wait a minute. Oh, yeah, 2030. Let's. I want to do a quick calculation. So let me see if I can pull it up here. So what we were suggesting, we said we took the, oh no. We took the 77.1, and we said times 1.16. 1600? Yeah. Let's see, what do we get? Every 10 years, right? 78.4. What am I missing here? Times 80 years later. Times 80 years. So let's see, because I know if I do 77.1 plus 0.16 times, it's been what, 10 years? Why is that other one off? Let me think about it. Okay. 10 years later. Okay. So I think the way we were thinking before was accurate, but the way we calculated was inaccurate, right? So the difference is the 77.1 was fine. And then I think I didn't account for the 10 years. Let me see, I think we needed a 10 in there. Let me back up here. Let me insert a 0. Let's see if that works. That's even worse. Wait a minute. Yeah, the only one that's really working, not that one, is this one, right? So I think the way we set it up before, we didn't account that was 10 years later. So to do that, the 77.1 is fine, right? And then 16 hundredths of a year times 10 years, right? And it's not exact, but that's a much better answer than what we got before, right? It's close to what they got. And it's off because, again, these are approximations. This isn't exact. Like, it doesn't increase exactly by 0.16 every 10 years, but it's approximately that much every 10 years. But the way we calculated it before, we weren't accounting for it being 10 years later. So that's why that was. An American man born in 2030 will have a life expectancy of approximately 78.4 years, right? Okay, that's fine. Man, we're only about like halfway through this, but that's okay. So estimation with graphs, line graphs. So line graphs are often used to illustrate trends over time. Some measure of time, such as months or years, frequently appears on the horizontal axis. Amounts are generally listed on the vertical axis. Points are drawn to represent the given information. The graph is formed by connecting the points with the line segment, right? So line graphs. The line graph shows the percentage of U.S. college students who smoke cigarettes from 82 through 2014. We're asked to find an estimate for the percentage of college students who smoke cigarettes in 2010. 2010, all right? So each of these tick marks, what is that, 4 years? So that would be 2010. So each tick mark is 4 years. So then 2010 is going to be here. And it looks like that's right in the middle. So then if that's 4, so that should be about 18%. Right? It looks like it's halfway between 16 and 20. So it looks like it's about 18%. So in 2010, approximately 18% of college students smoke cigarettes. Let me try this on this far side here. Maybe it'll perform. What's going on there? Oh, that's interesting. Let's try it over here. Maybe it'll behave better over here. Because it basically keeps clashing with like things I'm trying to show. So maybe it might fit over there, hopefully. Okay. I think I even have trouble with it at the top. Yeah, that doesn't work up there. And then on the bottom, it's going to clash with that. So let's try this over here. Okay. And here's, digital representation of what we experienced. Okay. So the line graph, I think it's the same deal. In which 4-year period did the percent of college students who smoke cigarettes decrease at the greatest rate? So notice it decreased from 82 to 90, and it also decreased from 98 on, right? So the sharpest decrease, let's see, in which 4-year period? So each tick mark is 4. So whichever has the steepest slope, negative slope. Oh, it looks like 2002 to 2006. Sharpest decline. This is again just an approximation. We're just eyeballing it. It looks like it's 2002 to 2006. Right? So this is the steepest of all the decreasing line segments, indicated the greatest rate of decrease are the years 2002 through 2006. Okay. So the line graph shows the percentage of in which year did 30% of college students smoke cigarettes? Okay, 30%. So 30%, you see it just above the 28. That highest year is 1998. 1998. You see it here. Okay. So in this example, modeling the cost of attending a public college, estimate the yearly increase in tuition and fees. Estimate the yearly increase in tuition and fees. So it sounds like find the slope. We can try the same technique of finding the slope like the previous, right? Like we did before, and this seems pretty steady. So the change in y over the change in x. So we can say the 9410. Let me break out my trusted Dusty Rusty. All right. So maybe we can do the 9410. Here, let's get it in one. 9410 minus 3349 divided by 2016 minus 2000. Okay. So it seems like each year is increasing by almost 380, right? $380 every year. Okay. So we got 378.81. 378.81. 378.81. So that 80 tells us to round up. So then 379. You see the 378.8, which is approximately $379 per year. So the average yearly increase is about $379, right? But they use the same technique, change the slope. So changing y over changing x, right? Okay. All right, let's keep going. So, if you're a student that's relying on these, it's a good idea to write down your questions. If anything is not clear, just write it down. You can email me again. If I don't respond by the next time we meet, then just ask me during class and we can pull these up and talk about it to clarify anything. Write a mathematical model that estimates the average cost of the function. Write a math model that estimates the average cost of tuition and fees, T, at public four-year institution for school year ending X years after 2000. Okay. So this seems to be fairly linear, right? I think we just found the slope. Let me see. So I'm going to fit it to a linear model. So what that means is I'm going to use y equals, hang on. Y equals mx plus b, right? We just found the slope in the previous, so I'm going to use that to be, I guess we can use the thing. Estimate, yeah, let's just use the 279. Is that what we found? 379. Okay. Let's see. I'm just going to choose a point to solve for B. So I'll plug in the first point. That one looks fairly simple. So then, yeah, if I could just collapse it. That's like irking me. It feels like it's so distracting. So let's see. For a slope of 379, that for the first year being 2000, whoops, that's not a 2000. We're solving for B. The corresponding tuition and fees is 3349. Okay. So then using algebra, we get that B equals, we're going to say it is 3349 minus that result. Right? Okay. So if we say 3349 minus 379 times 2000, okay, that's fine. So then a y-intercept looks like it might be negative 75,000, nope, 754,000. $651. Let me think about this. Okay, that might be the case. So let's just go with it for now. So then our model, it looks like it's going to be y equals 379x minus 754, 651. Okay. The average cost and fees, T. So if we want to put the right units, the tuition should be equal to 379 X years after 2000. Now, we might be able to augment this if we let 2000 be year 0. Okay, yeah, let's do that. I feel like that's going to be a lot better. Let me back up some. So I'm going to let the year 2000 be year 0, right? If the year 2000 is the year 0, then we can replace this guy with a 0, right? And I'll do this in like red or something. So we're going to let the year 2000 be year 0. Then what happens there is that our y-intercept becomes 3349. Okay, so we'll do that here. 3349, right? So now with that, if we decide to go with that model, then we're going to get y equals our slope, which is the 379 times x plus the 3349. That's much better, right? And this is based on years after 2000. And so then the tuition and fees should be 379x plus 3349. All right. Again, we just let the year 2000 be year 0. Okay. Let's go. Let me see. So write a model that estimates the average cost of tuition at a public four-year institution for X years after the year 2000, right? So again, we went back, you see in red on the left-hand side, instead of putting the year 2000, we let the year 2000 be year 0, and that adjusted our model, right? So you see the 379x plus the 3349. Okay. Then we're asked to use the model to project the average cost of tuition and fees for the school year ending in 2020, right? So then, so that's 20 years after the year 2000. So then we would just put a 20 into this model, right? So let's do it a little bit different this time. Let's go to our y equals. We got 379x plus this 3349, right? So now if I want to do 20 years later, what I'm going to do, I want to call in that function I just typed in. All right, so I'm going to the left of the clear button is a button that says VARS. I think that's short for variables. I'm going to click on that. I'm going to go to the right to go to Y variables. I'm going to click on number 1 for function, number 1 again to call on that function I typed in. And I will do open parentheses. And so we said it's 20 years later, so our X is going to be a 20 and close parentheses. And our approximation for tuition and fees is $10,929. $10,929. Okay. Okay, so let me go ahead and make a copy. Let me make a copy of this available. Now in hindsight, I don't know if I made that first one available. I don't think I did. Okay. Paper recordings. So when this bar finishes loading, you want to click on that box link that I put in the announcements to access this. And you've basically gotten a copy of any writing that you saw me do. I'm gonna go back and go ahead and load. Matter of fact, let me just go ahead and do it now. This one, the first one, I just realized I didn't make it available. So I'm gonna go ahead and share, send it to box, and you can go to the same location, send a box, right? So again, when this bar finishes loading, now you'll have a copy of what we did in the previous section along with this section. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Section 1.3 will be up momentarily. Take care. Peace.